Hello guys, good day. For today's video, we will going to discuss Chapter 6 Memories. First, meet our group, Diana, Michael, Dave, and Nerby. Now we are going to discuss what is memories. A memory is just like a human brain. It is caused to store data and instruction. Computer memory is the storage space in the computer where data is to be processed and instruction required for processing are stored. The memory is divided into large number of small parts called cell. Each location or cell has a unique address which varies from 0 to memory size -1. A digital memory is an array of binary storage elements organized so as to provide some means of external access. Memory array is arranged as a set of memory words, each of which consists of a number of a single bit storage element or memory cell. A memory word has a length of 1, 4, or 8 memory cell and can store 1 bit, 4 bit, or 8 bit, or a byte of information respectively. The content of a particular memory word are accessed by specifying a unique memory addresses. Memory address is a normal decoded from a binary number. There are usually 20 memory word in array. Memory capacity, which is measured in bit, it is given by the product of the number of memory word and the number of memory cell in each word. Memory capacities are frequently defined in bits, where 1 kilobyte is equal to 210 or 1024 bits. There are two basic ways of organizing the memory array to allow external access to the store. First is the serial or sequential access, where the time to access a particular memory word is not constant but depend on its position in the array. The second one is the random access, where the time to access a particular word is independent of its position. Access time is defined as the time delay between providing a memory address and gaining access to the stored information, or completing modification of stored information. The speed of operation of a memory array is sometimes defined in terms of its cycle time, which is the maximum allowable time interval between the initiation of successive memory access operation. There are different techniques for storing binary information. The memories commonly used in microprocessor system are based on one of two storage techniques. One is the magnetic storage. Magnetic store are non-volatile and retain the stored information when external power supply are disconnected. The second one is the electronic storage. Electronic or semiconductor store are, with one exception, volatile and require the continuous connection of external power supply if the stored information is to be retained. There are types of magnetic store. First is the magnetic core memories. The core memories have short access time. They are uneconomic to manufacture for small memory capacity sizes. Typically, the smaller commercially available core memories have capacities of 32 kilobytes and their application is usually limited to data and program store in a relatively large microprocessor system. The second one is the magnetic surface memories. Magnetic surface memories have longer access time but provide a low-cost, large capacity, non-volatile storage medium. Magnetic tape, cassette, and magnetic flexible disk memories are the most common secondary stores for data and program in microprocessor system. There are two major advantages over magnetic core memories. First is they can be manufactured at a compatible cost or bit for small capacity unit, which can be assembled to meet the exact storage requirements of a particular microprocessor application. Second, they are electrically compatible with the microprocessor chips and they are more easily interfaced to the microprocessor system. Semiconductor memories. The use of semiconductor memories in microprocessor system is widespread. Semiconductor memories fall into three categories. First, read and write memory. Second, read-only memory. And third, read-mostly memory. Read-write memory. The content of read-write memory may be read out or modified an unlimited number of times under external control. The read and write access time are of similar length. Read-only memory. In read-only memory, the content can be read out but after they have been initially defined, they cannot be modified. Read mostly memory. In a read mostly memory, the content may be read out but modified only, with considerable difficulty. In this case, the write access time is many order of magnitude longer than the read access time. In addition, the number of times that the stored information can be modified is often limited. The basic read-write memory cell. Most read-write semiconductor memories are manufactured using either bipolar or metal oxide semiconductor or MOS technology. Bipolar memory cells are static in that they retain the stored information as long as the power is applied to the circuit. MOS memory cell can be either static or dynamic. Even with the power applied, a dynamic memory cell can only store information for a limited period of time, typically 1 or 2 ms, and required its content to be refreshed from time to time. In dynamic metal oxide semiconductor memories, there are two important advantages over static memories. First, the standby power, which is power consumed by the circuit when read or write access operation are not taking place, is much lower. Second, the number of transistors per memory cell is smaller. Thus, larger capacity memory array can be manufactured on a single integrated circuit chip at lower cost. Bipolar static memory cell. In the figure, the two multiple emitter transistors are cross-coupled to form a simple bistable latch. The connection to the emitters allow the cell to be selected and data to be entered or read out. P or N channel MOS static memory cell. In the figure, two of the transistors are cross-coupled to form the bistable latch as before, which the other are used for loads and for the gating logic which allow access to the cell. MOS dynamic memory cell. In this figure, the MOS dynamic memory cell relies on the temporary storage of information as charge or lack of it on the gate capacitance of an MOS transistor. Organization of serial access read or write memory arrays. In a serial access read or write memory, the sequence in which the information is loaded into the input of memory will determine the order in which the stored information is available at the output of the memory. Access time are therefore dependent on the memory location. The first in first out, FIFO memory. The memory consists of a number of chips register equal to the number of cells in the memory word. As shown in figure 6.3, each chip register, which is formed by interconnecting a string of memory cells, is clocked from the same source. At every clock pulse, the content of each column of cell is transferred one position to the right. new information is entered into the first column of cell and the oldest information is read out from the last column of cell. Entry of new information will lead to the loss of old information from the memory. Both static and dynamic memory cell can be used in the construction of the shift registers, and the shift operation is usually controlled by a multi-phase clock. 3-phase MOS static shift register cell. As the figure shown, a memory cell from a MOS static shift register which uses a 3-phase clocking sequence. The new data is read into the left-hand side and the old data is read out at the right-hand side of the cell when theta is high. The circuit operates dynamically during the shift operation and relies on gate capacitance for information storage. When theta 2 and theta 3 are high, the transistors are fully cross-coupled. The information is actively latched and the cell operation statically until the next clocking sequence begins. It is common for theta 2 and theta 3 to be generated on chip from theta 1. The maximum clock rate will depend on the charging and discharging time consists of the circuit. There is no minimum clock rate. A typically MOS static shift register has a capacity of 2 kilobytes or chips and a maximum operating frequency of 2 MHz. 2-phase MOS static shift register cell. As shown in the figure, a cell from a dynamic MOS shift register which uses a 2-phase clocking sequence. The cell consists of two similar circuits interconnected as a master-slave combination. The cell consists of two similar circuits interconnected as a master-slave combination. New data stored on CGI is sampled when theta 1 is high and its inverse is stored on CG2. The data output line is set to the inverse of the data stored on CG2 during theta 2 to complete the shift operation. The standby power dissipation is low since the load transistors are switched on only theta 1 or theta 2 are high. Periodic clocking is required to renew the charges on CGI and CG2. The minimum clock rate will be determined by the rate of charge leakage from the gate capacitors. The maximum time that inform can be retained in the memory will depend upon the length of the shift register and the minimum clock rate. The circulating memory. A circulating memory is a PIPO memory with its output feedback into its input. In this figure, some additional logic is required to allow new data to be gated into the memory. If the memory is constructed from dynamic shift register, the circulating operation provides a means of automatically refreshing the dynamic store. In standby mode, the contents are continuously recirculated at a rate determined by the clock. In read or write mode, the content of the encountered are compared with the address of the desired memory word until a match is found. The write or read control signal then gets the required data in or out of the memory. The access time varies according to memory location. It has a maximum value dependent on the length and clock rate of the memory. Random access read-write memories. In a random access read-write memory, the availability of the stored information at the output of the memory is independent of the order which the information was loaded into the memory. Access time are therefore independent of memory location. The standard random access read-write memory consists of a memory cell array with memory addresses, decoders, data sense amplifiers, output buffers, and access control logic, all on a single integrated circuit chip. The term RAM is generally accepted to describe this type of memory, although other type of random access memory are in common use. Memory arrays are based on bipolar or MOS static memory cell or on MOS dynamic memory cell.
Hello! Ako nga po pala si Michael Dave M. Lachica. Ang nagbigay po sa aking topic ay two ways of organizing memory address decoding. Word organization. A multi-byte memory word structure is used in the array. A single binary address decoder is used to select simultaneously each of the memory cells in the particular memory word which has been addressed. The number of external connection to the integrated circuit package is high and the technique is only used is small capacity memories. Coincidence addressing. In larger memory chips, the number of external connection is reduced by adopting a single bit memory word structure for the array. Two decoders are used to generate the X select signal and the Y select signal from the binary memory address. A particular memory is cell is accessed when both of its X and Y select lines are active at the same time. The logic the logic to detect a coincidence of the select signals is either included as a part of memory cell figure 6 to 8 or is implemented using gating circuits external to the array figure 6 to 9. Coincidence addressing. Most of the commercial available RAM chips include chip select logic and use three state bidirectionally data line under control of a read or write select signal to simplify the design of large multi-chips. Memory systems. The number of words in a memory array may be increased by connecting the outputs of several memory chips in parallel as shown in figure 6 to 10. The number of cells in each memory words of an array may be increased by paralleling address and chip selects lines of several memory chips shown in figure 6 to 11. A typically bipolar static RAM chip has a capacity of 256 bytes in a success time of 50 ohms. A typically most static RAM chip has a capacity of 2 kilobytes and a success time of 40 ohms. Most dynamic RAM chips have larger capacity, 4 kilobytes and similar access times but require additional external logic to control the refresh operation. In most cases, refreshing accomplished by performing a read or write operation with the chip select disabled on each column of the memory array in turn. The refresh operations must be organized so as to cause a minimum of interference with the normal memory access operation. Content addressable read and write memory. A content addressable read and write memory (CAM) is a random access memory with additional logic included at each memory cell to allow direct comparison of the contents of the cell with the externally supplied data. CAM three modes of operation: read, write, match. In the read and write modes, the CAM function in the same way an ordinary random access read and write memory. In the match mode, the additional cell logic is used to compare the information present at the data input lines with the contents of the address memory word. The content addressable memory provides a powerful tool for microprocessor application involving data search operations. Read-only memory. A read-only memory ROM is an array of memory cells whose contents are predetermined to stored information is defined by physical layout of the memory array circuits, which in the provide inviolate store is word of the memory can be accessed at random and its contents read out by selecting a unique binary address. ROMs UA but words organized and coincidence addressing schemes to decode the memory address. Although information cannot be written into the memory, the external characteristics of ROM chips are functionally identically to those of the RAM chips. There are some ROM and RAM chips which are the both electrically interchangeable and pin compatible. The memory cells in a RAM array are simpler than in a RAM array since its contents are unchangeable. Typically, the basic cell in a ROM array consists of a single diode or transistor. The stored information in an MOS transistor ROM is determined by the presence of or absence of an electrical connection between the gate and the row select line at each node of the array. In bipolar transistor ROM, the stored information is determined by the presence of or absence of an electrical connection between the emitter and load resistor. The byte pattern held in the RAM must defined at the time of manufacture. Either a custom design integrated circuit is a manufactured or is a standard integrated circuit is manufactured and programmed at the last stage of fabrication with the desired byte pattern to produce a mass program ROM. In the latter process, unconnected the diodes or transistor are fabricated at every node position and then a special purpose metallization. Mass is used to interconnect the components according to the specified byte pattern. The mass program ROM offers an economic method of manufacture when quantities are too small to consider custom design integrated circuits. Typically, single chips bipolar ROMs have a 1 kilobyte capacity of 4 ounce access time, while most on ROM have 16 kilobyte capacity and 40 ounce access time. User or field programmable read-only memory. The user programmable read-only memory PROM is a ROM chip whose contents can be specified after manufacture by external application of electrical signals. Two types of PROMs: fusible link from unbalanced induced from. The fusible link from an integrated circuit containing a bipolar or MOS or ROM array is manufactured with all transistors fully interconnected so that the memory initially stores all 1 or 0 in each cell. In a figure 6 to 17, critical interconnection is made each node position to fusible metallic or semiconductor link. The link can be destroyed to break the connection and change the state of the cell application and an abnormally large current to the appropriate part of the memory circuit. The state of the cell cannot be modified once the associated link has been fused. The programming operation is performed in a special purpose programmer which addresses a specified memory word and destroy the fusible links according to the byte pattern specified by the user. The programming of the enter contents 1 kilobyte from chips may take several minutes. Number 2, the unbalanced induced from. And the unbalanced induced from is a based on the bipolar from array and is manufactured with all transistors fully connected by applying large external voltage unbalance breakdown and can be induced through the base emitter due conjunction junction of the transistor in any particular cell. A large reverse current flows the junction fuses and shorts out to the base emitter connection to change the state of the cell. The programming is performed is special purpose from program as before. Read mostly memory. One type of read mostly memory which is widely used in a microprocessor system is the user reprogrammable read-only memory REPROM. The REPROM is a read-only memory which can be electrically programmed, erased, and reprogrammed several times. The most common type of floating gate balance injection most FAMOS REPROM. In each memory cell, the information is stored as the presence or absence of charge on the gate of most transistor. With the power of supplies disconnected or under normal operating condition, the gate is electrically isolated from the other parts of the circuit and no charge leakage can occur. The PAMOS or reform can retain the stored information for a long period of time, at least 5 to 10 years. During programming, abnormally large voltage are applied to the circuit. Avalanche breakdown of the diode junction allow charge to be injected into the isolated or floating gate of selected memory cell. The programming operation which is performed in a special purpose from programming might take 2 to 3 minutes to load the contents or an entire reform chip. The programmable logic array. The programmable logic array PLA is a general purpose integrated circuit which includes both read only and read write memory cells on the same chips. Initially, the chip is fabricated with the various circuit elements and connected by specifying a final mask. In fabrication process, the PLA can be interconnected to perform special purpose memory function. The incorporation of the combination and sequential logic elements in the same chips provides a flexible and powerful semiconductor memory element.
Uses of memory in a microprocessor system. Memories play a fundamental role in all microprocessor systems and have a number of different uses. Each type of application has particular requirements which will determine the most suitable kind of memory. There are 6 important applications of the uses of memory. 1. Main program memory. Number 2 is the microprogram or control memory. Number 3 is scratch pad data memory. Number 4, main data memory. 5, secondary data memory. And last, input or output device memory. So let's talk about the main program memory. The size of the main program memory will vary greatly depending on the microprocessor's application. Typical capacities range from 512 bytes to 16 kilobytes. The basic requirements are number one, non-volatile storage and a read access time compatible with the normal operating speed of the microprocessor. The most common type of main program memory are mass program ROM, PROM, REPROM, or ferrite core memories. Dynamic MOS RAM with a standby battery power supply to guard against power failure is also used. Programs are often developed in volatile static RAM chip, which are subsequently replaced by pin-compatible PROM chips. REPROM has obvious advantages during program development. Next is the microprogram or control memory. The control memory of a single chip microprocessor is situated on the microprocessor chip itself. The main requirements are non-volatile storage, high speed, low power consumption, small chip area per cell. The microcode will be stored in a ROM which is designed to meet these requirements and is fabricated using the technology of the microprocessor. High speed and non-volatility are the important consideration when choosing a suitable external control memory for a bit-sliced microprocessor. A mass program bipolar ROM is commonly used. The third important application of the uses of memory, the scratchpad data memory. So, scratchpad memory is used as a temporary data or address store during the execution of an instruction or as a short-term intermediate store during the processing of data. In some microprocessor, the scratchpad is structured as a number of internal working registers. The main requirements here are high speed, low power, small chip area per cell. A dynamic MOS RAM is often used. A microprocessor using dynamic data storage has a minimum system clock frequently to ensure adequate refreshing of the data in a scratchpad registers. The maximum number of machine cycle which may be stolen during DMA operation is also limited. There are no such registration in a microprocessor which uses a static RAM for the scratchpad memory. Some microprocessors use an external scratchpad memory. The most important consideration here is the speed, and a bipolar static RAM is commonly used. Next is the main data memory. In most microprocessor applications, the size of the main data memory is small in comparison with the main program memory. Large capacity, high or medium speed data memories are sometimes required in microprocessor-based data acquisition systems where large quantities of data must be stored in relatively short time periods. In these applications, MOS static RAM and ferrite core memories are frequently used. MOS dynamic RAM memory systems are also used. In particular, they find application in large capacity memory systems where the total power consumption and heat dissipation can be considerable. In some systems, a small high-speed memory is used as a buffer store between the microprocessor and the slower large-capacity main data store. Blocks of data can be transferred from the main data memory to the buffer or cache memory under external control so as to ensure the high-speed memory always contains the data most relevant to the current microprocessor task. A bipolar static RAM is the obvious choice for cache memories. Next is the secondary data memory. A secondary memory or backing store is used as a long-term semi-permanent data store in a microprocessor system. The main requirements are non-volatile storage and large capacity at low cost. Access time from 5 ms to 100 ms are usually acceptable. The most common secondary data memories are magnetic tape cassette or magnetic flexible disk store, although the cost of semiconductor recirculating memory systems with battery-driven standby supplies is becoming increasingly competitive. Last important of application of the uses of memory, the input or output device memory. The microprocessor and its input or output device usually communicate asynchronously. A temporary data store is often required to hold information during input or output operations. These input or output buffer memories, which are frequently included on the input or output interface chip, are usually of small capacity. In a memory map microprocessor systems, the input or output buffer memories are accessed in an identical manner to the main data memory. Most input or output buffer memories are based on the MOS static RAM. So let's move on to the use of static RAM in a volatile read or write memory system. The memory array consists of two banks of 8 1K times 1 bit static RAM chips. The 10 low-order bits of the address bus drive the memory address inputs of each RAM chip in parallel through a set of bus buffers. The 6 high-order bits of the address bus together with the valid address signal are decoded, according to the memory map of the microprocessor, to generate two chip select signals, one for each bank of 8 memory chips. The bidirectional data bus is connected to the data in and data out lines of each RAM via bidirectional bus drivers. The mode select logic generates the read or write select signal for the RAM chips and control the direction of data flow through the data bus drivers. Synchronous memory control. The microprocessor expects the memory to respond to a memory access request within a defined time interval. Data may be lost if the memory cannot respond in the required time. So, there are three ways of controlling data transfer when using a slow memory. Number one, the frequency of the system clock is reduced until the microprocessor and memory operating speeds are compatible. Additional data transfer control logic is not required. And number two, the system clock period is lengthened during each memory access operation. The data transfer control logic generates a slowdown signal which causes a temporary reduction in the system clock rate. And last, number three, memory data transfer is treated in the same way as input or output data transfer under program or interrupt control. The data transfer control logic responds to and provide the necessary control signal to interact with the microprocessor during input or output operations. Asynchronous memory control. After it has requested memory access, the microprocessor pauses with the operation suspended until a memory-ready signal is received from the memory system. The data transfer control logic generates the memory-ready signal from the delayed version of the memory read or write request signal. The delay is adjusted to suit the particular access time of the memory chips. Next is the fourth section of memory system. Number 1. The memory array. The array consists of two banks of 8 4K 1-bit dynamic RAM chips. Each chip is organized as a 32-column by 128 row matrix of cells with the column address generated from the lower 5 bits of the memory address. Refresh is achieved by addressing a particular column of cells and initiating a memory write operation with the chip select disabled. Each of the 32 columns of memory cells requires refreshing every 2 ms. Number 2. Chip select and address decoding. During normal memory access operation, the 12 low-order bits of the address bus drive the memory address inputs of each RAM chip. The 4 high-order bits of the address bus together with the valid address signal are decoded to generate the two chip select signals. During refresh, the column address is generated by the refresh counter. Both of the chip select lines are disabled and the memory write mode is selected. During power failure, CMOS low power buffers are also used to isolate the memory array from the control signals, which are normally derived from the microprocessor bus. The address multiplexer and other parts of the circuit which must remain active during the power failure are also realized using CMOS technology. The third section of memory system, the refresh control. Refresh is performed on a cycle-still basis, one column at a time, under control of the refresh control logic. The refresh clock increments the refresh counter and initiate a new refresh operation every 62.5 µ per second. After gaining control of the memory by raising the refresh request signal, the control logic disable the chip select lines and initiate a memory write operation using the contents of the refresh counter as the memory address. Memory control is then handed back to the microprocessor. The refresh logic, which must operate during power failure, is realized using CMOS circuitry. Next is the power fail detection and control. The power fail line is activated immediately a failure in the main power supplies of the microprocessor system is sensed. The power fail logic allows completion of any current memories access or refresh operation before generating the standby signal, which disable the chip and read or write select buffers and connects the standby clock to the memory array. The memory refresh control logic continues to operate normally as it derives its power from the standby supply. The total power consumption of the memory system during power failure is typically 200 milliwatts. If it obtains all voltage level from a single 12-volt battery of 4.5 ampere per hour capacity, the memory system could be supported in standby mode for some 8 or 9 days. That's it for today's video. See you again next time. Bye.